So we are going to start with a very interesting topic called as linear algebra. Now you might be thinking why, right? Uh, so linear algebra is one of the most fundamental thing which you will be using in your machine learning a lot. Now, you might be thinking why? Means you used to study all this during your school days a lot, and you might be wondering now that why now I have to read all these things. Basically I have already come out of that stage, and still do I need to read all these things? Yes, answer is definitely yes. Let me give you a intuition that why basically we need this. So first of all, linear algebra, when we say, we mainly think about matrix multiplication, multiplication. You can also talk about vectors, eigenvectors, okay, eigenvalues, but they are anyway separate. So like vectors, so they are like a backbone for all your numerical analysis libraries which are present in your Python. Now, beside almost all the machine learning algorithm which you're gonna use is going to use linear algebra behind the scene. Okay, so with this itself, you can make out that how really important this topic is going to be. Like every machine learning algorithm which you're gonna learn will be using linear algebra at the back end. So the understanding is really important for it. Now, what we will try to learn from here is we will try to develop that intuitive understanding of all the concepts. For example, we will try to learn about vectors, dot products, linear transformations, and so on. So we will try to learn all these things, but the fundamental question still is there: why? Right? Why these machine learning algorithms are using my linear algebra at the backend? Means any reason behind this? Yes, number one point is, if you think about any of the visualization right now, let's say you are living in a 3D world, right? You are living in a 3D world. Now if I plot, let's say in front of you, a plot between x and y, so you will immediately say that okay, I'm going to visualize this data in my 2D plot, right, in a two-dimensional data. Now the same thing I could have just gone, let me make this y properly, y. The same thing, if I add one more dimension to it, let's say I add one more dimension z to it, right? The plane in which I'm living in. Now you can say that it's a 3D world, right? Like what you are also seeing it in terms of you is a 3D world, what you kind of look at. Now, so if I ask you, can you explain me about 4D word or 5D word or ND word? Now would you be able to give me any visualization diagram or any visual representation of it? No. Now it will become difficult for you to handle such scenarios. And in your machine learning algorithms, when you are going to work on your machine learning algorithms with the data given to you, most of the times you will end up with algorithms or basically which you are going to work on the data, which is going to be n-dimensional data. It's yes, you will definitely be working on two-dimensional, three-dimensional as well, but most of the time in practical world when we are going to work, you're gonna work on n-dimensional data where n is going to be greater than 3. Now in those places, definitely my linear algebra is going to help me. Linear algebra will help me in extending anything from a 2D word or 3D word to ND word. That is what my linear algebra is going to help me. So I can say that my first point is, it is going to give me an intuition and visual representation of my building block. So that is what going to be very helpful. In fact, when I will be talking about in machine learning like kernels in SVM, kernels in SVM. Right now, you need not really bother about it if you are not knowing all these terms, because we're going to learn all these things. Or basically, if I talk about SGD, which is also called as stochastic gradient descent, which you are going to use basically in neural network, right? Now, basically here you will be using linear algebra a lot because you would like to understand or basically the data by visualizing the data into multidimensional spaces. So but without linear algebra, understanding of these concepts would be almost impossible. Okay, so that's basically the first point. Second point, this is the first point for your linear in the favor of linear algebra. Second point. Second point is working with algorithm. This is again related with the first point itself, but a little different. Now, when you going to create a statistical model using a computer, or when you were looking at the coefficient of weights of your models, they are all being calculated using linear algebra. So while working on like simple line equations, like which you're gonna learn in some few minutes itself, like y is equal to mx plus c, right? Now we have a lot of coefficients basically coming up. Now, this coefficient or these weights, what we're gonna have, play a very major role in machine learning algorithms. So that's where basically this becomes very important. So you need to understand how this matrix multiplication happens and how we can represent all these things. Now, second thing is when you are solving all this machine learning algorithms, you will notice that you will have some unknowns. For example, here you have one unknown here, one unknown here, right? So you will have like a lot of unknowns coming up, and you will have multiple equations also. Now let's say you will have two unknown and two unknown equation, like or basically you have n unknowns and n basically equation, algebraic equation for this. Now using this you will be computing using those basically equation, the matrix equation what you're going to create. You would like to go ahead and solve those unknown values. So that is also requiring a better understanding of the linear algebra, because this is something which will be very important. And not only this, a lot of times it do happens that you will end up in a job where you might have to create your own algorithm completely from scratch. Now there you need to effectively use all the libraries and so on, and this is again where you would be using optimally this basically all this linear algebra knowledge what you're going to learn in this particular course. Now one thing, I would keep this linear algebra up to an extent which you will be needing it for your machine learning algorithms. Now, definitely linear algebra is a wide topic. I can deliver a full-fledged course on linear algebra on this, but I will not go into each and every component of it, because it is not going to make any sense also for us to go ahead and look at each and every component. But yes, from the machine learning perspective, whatever knowledge we need, we gonna cover that within the class so that you have a good insight of it. Second thing is, at few places what I will do, I will relate all this linear algebra with your in your Python code. So what I'm going to use, I will be using my NumPy package which you have learned in your previous section. Now NumPy package I will use and show you that lot of things related to vectors and multiple other factors with linear algebra, we will be writing code for it. So I will also show you up so that you can kind of link all these things and can understand that after understanding the concept, how you can even create all these things in the Python part, right? So that will make things even more interesting. Now, so let's start. It's a very interesting topic, guys. In fact, I love this particular topic. I don't know why people used to say that it's one of the boring subject, maths, but it's not, because it's if you understand linear algebra intuitively, it is really a very simple subject to go with, and it is very highly interesting also, and that's what makes machine learning also very interesting, because machine learning is relying on the concept of this linear algebra. So this is going to be very important. Now the first thing which comes in our mind when we talk about linear algebra is vectors, right? The first thing which comes in our mind is vectors. Now when I say vectors, the first thing which comes again in my mind with respect to vectors is that whenever something have magnitude and direction as well, then we define that entity as vector, right? This is something you can recall from your basically school days and so on, right? Now there are different way people kind of represent a vector. Okay, so people have very different views. If you ask them about vectors, I will talk about them, that what are these things. So like some people go in the geometric way, some people try to represent vector in algebraic way. So there are various ways you can represent basically a vector. So let's say if I do take I say a vector m, so I always represent a vector with an arrow symbol which denotes that it's basically is a vector. Okay, so because there is also something called a scalar. Now scalar do have only a magnitude but no direction to it. So I don't put this arrow symbol. So to represent a vector, I will always put this arrow symbol just to represent that yes, it's a vector. But going further, I would remove it, not to always call it up like this. Now, if in a given vector, okay, I have to put some values. Let's say I have a vector A and I want to represent some value. Let's say I would say like how much marks I scored in my basically in my math subject. So let's say I scored 35 in my math subject. I know it's very less, but let's say this is 35 out of 35. Now it makes sense, right? Now second subject was physics, where I scored maybe 32 marks, right? And basically if this I have to represent, this means that I'm talking about a two-dimensional vector. So whenever I say dimensions, you can relate in this vector in this manner as well. So here the values which I have kept basically is a vector where I'm keeping some data to it, and there are two entries which I have kept in it. That's the reason I'm going to call it as a two-dimensional vector in this case. If I have to represent also my vectors into a format, I can always represent my vector in a 2D dimension like this. Let's say I want to represent a value, let's say 35 comma 32. I can always do that like this. I have, let's say, on my x-axis the value 35 here, and basically on my y-axis I do have a value 32 here, and I can represent it in this particular format. So in this case, this is my a vector which is present in my 2D space in this manner. Now let's say I add another subject, because let's say this was related to maths and this was related to physics. Now I want to add one more thing to it, right? Let's say I want to add chemistry to it. So let's say I'm going to denote a vector b, and this time I'm going to say 35, 32 and 33. Now this becomes my chemistry marks. So now if I have to represent it, I definitely cannot do it in a 2D plane. Now I have to do it into my 3D plane, right? So now this will be three-dimensional vector, and in this three-dimensional vector I would be able to represent it quite easily by just denoting vector b and gonna say that whatever the point is coming up in this 3D space, right? So that's what I can always do. Now this is about 2D vector and 3D vector. But what about if I have to talk about ND vector now, right? N dimensional vector where my n is, let's say, greater than 3. Now in that case it's quite simple, though I will not be able to draw a diagram here to represent it, but at the same time I will always be able to represent my vector definitely into an n dimensional format. I can say that vector C, and I will say 32, 35, 33, 31, 30, 35 and so on. So you can see that here 1, 2, 3, 4, 5, 6. So this becomes a 6-dimensional vector. This becomes a 6-dimensional vector, what is there in front of us. So can you see a beauty of your linear algebra? Maybe you are not able to visualize something right now in the real world, but at the same time I'm definitely able to put this into my vector notation, and I'm able to represent an n-dimensional point in form of a vector. This is quite interesting thing when we talk about basically with respect to our vectors. Now if we have to represent these vectors, we do define our vectors in this format as well. So let's say since I have to define this value, so this is going to be your origin, okay? This middle point is going to be origin. Let's say I have a vector a, okay? So I'm going to represent it by vector a. Now there are few things being linked to this vector. Now number one thing is there is a length of vector. So length of vector can be denoted like this. So whenever I will be using this double thing, this means that I'm talking about the length of this. Second thing is this angle which this vector is creating from this axis. Let's denote it as by theta or phi, whatever I want to. So this is also one thing we have to say. So this is basically what denotes your magnitude, and this is what denotes your direction. when I was talking about vector do have a direction as well as magnitude present in it. Now, second thing which is also important to understand here is, now when I have already talked about this vectors and all, now definitely a question comes up. Let's say if this vector A have the value a comma b, and if I want to find out that what is the distance of vector A from the origin, right? So how I can do that? So this is origin, so it's gonna be 0 0. So I can always use my Pythagoras theorem, because if I've represented this point as AB, that means this is going to be your A, right? This is going to be A, means this distance is A, and this is going to be your B, means this distance is going to be B, right? So if I have to basically talk about this using the Pythagoras theorem, I can easily say that it's gonna be A square plus B square, right? That's basically denotes the distance of this, which I can also represent it as length of my vector A, right? I can also represent it like this. Now, what about, like in the last example, when I was talking about, let's say, 3 subjects marks, and we have said that it's a 3-dimensional vector. So in that case, how can I represent it? So I can always go and say that, okay, I'm gonna just add another term to it, which is going to make it like a square plus b square plus c square. So whatever the third vector value is there, you can always just square it up and do it. Now, don't you think it's making our life very simple now? If I have to represent the same thing or extend the same thing to my n-dimensional array, now, don't you think it's quite simple? I can simply say, just like how I was doing this, I can say that a1 square plus a2 square, and I will keep on doing it till an square, right? Can you again see the beauty of your linear algebra, where I am able to represent again a 2D or 3D dimensional very easily with respect to my n-dimensional data, right? So this is how I can do it. So in short, I can represent it by stating that if I have to represent the length of vector A, I can always say the value of ax square plus ay square, and basically taking the square of it. This is what we just learned. Or right, so ay basically is nothing but your y term, right, where I was saying b, I have represented it by term a and b. Now if I have to represent in terms of angle, if you remember from your trigonometry, I have a tan theta basically part, where I can say ay and ax, basically the y coordinate of a and x coordinate of this. So I can also represent this theta or phi, whatever I want to denote to, as arc of tan, and I can just define it as ay divided by ax. Sometimes we denote arc of tan as tan inverse like this also. That's also fine. Any way you want to represent is okay. But the main intuition should be kind of clear to you, that what we are trying to do in this particular space, what we are trying to basically achieve in this space. Now, let's look at, if I have to calculate the distance between any two particular vector points, how I can very easily do that. So let's say, because these are the problems which will keep on coming when you will be working on your machine learning algorithms. So these are very basic things which will keep on coming up, and you have to always basically answer them up with the help of linear algebra. So anyway, I will again first start with a 2-dimensional, move to 3-dimension, and then take it to the n dimension in this case also. So let's say I have a point A, okay, and let's say this have the value of a1 comma b1. Let's say this is my vector A, which contains this point. I have a vector B which contains b1 comma b2, right? So let's say I have to find the distance between these two. Let's say this is what I want to figure out, right? Now if you basically look intuitively, right, what we gonna do in this case is we can use Pythagoras theorem. I can always go ahead and use this Pythagoras theorem. So if you look at the Pythagoras theorem, this value will become a2 minus b2, this part, right? And this part, if I want to write it up, it will become b1 minus a1, right? You can easily look at this and do it. So this will become b1 minus a1. Now using this Pythagoras theorem, I can always go and write my equation where basically this is what going to be a1 minus b1 whole square, basically this part, plus a2 minus b2 whole square, right? So this is what my Pythagorean states, right? That this value, this is because this is a triangle. So I'm basically writing this format and be able to do it. Now, same thing if I want to expand it to 3D word now. So how can I do it? Let's say I have a point P which have A1, B1, oh sorry, let me note it as A2, in fact, will be more easy, A3, okay. Similarly, I have a point Q which have B1, B2, B3, right? And I have to find the distance between these 2 points which are present in a 3-dimensional data now. Now again it's quite simple, right? Again the same way, I can say A1 minus B1 whole square, these 2 points, plus A2 minus B2 whole square, these 2 points, plus A3 minus B3 whole square. That's it. Now, if I ask you to follow the same thing in an n-dimensional data, I would suggest you to pause my video right now and just see whether you are able to get to that answer. It's quite simple. In an n-dimensional data, if I have a point P which is running from A1, A2 till AN, and I have a point Q which is running from B1, B2 and till Bn, and if I have to find the distance between these 2 points, I can take the square root of, and I have to run this from 1 to n. Ai minus bi means keep on taking the first term, then second term, square it up and summing up all these values, and you will get basically your output. So this is the way you can always go back and create your vectors distances quite easily in this manner. Now, so we just learned about how to basically create all these things and all. That's all good. But sometimes we do want to represent something called as unit vector. Now, what is a unit vector? So if I have to talk about a unit vector is nothing but which have the magnitude of 1, means the length of a unit vector is always going to be 1. Okay, so that's what we will always represent here whenever I have to define unit vector. Unit vector, you can basically always define it as well with respect to a hat. Okay, let's say I have a vector a, and if you divide it with the length of a, you will get a unit vector. So in unit vector, the property is, let's say if this is the case and let's say this is my vector a, okay. So what we do in unit vector, we go with the same direction, Only difference would be that my magnitude will turn out to be 1. That's it. That's the only thing which basically comes with respect to unit vector. And this is a very important concept because we will be using in terms of vector span and so on while working on your unit vector stuff. Now, this is about your unit vector. Similarly, there are few more concepts which should you be aware of because I will be using this again a lot in your machine learning. One thing is called as row vector. Okay, so there are two kind of vectors which we have. One is your row vector and second is your column vector. In fact, this is going to be the backbone of all the machine learning data sets because this is how we're going to represent any data set and kind of will do a lot of computation. So if I have to talk about a row vector, first let's start with a row vector. So in a row vector, what we're going to do, if I define, let's say only one row, okay, let's say like this. If I say that value is going to be A1, A2, A3, A4 till AN. Okay, all these values there. Now this is what I have. How many rows in it? One row. How many columns are there in it? N columns. This is going to represent your row vector. In a column vector, it just go reverse. Okay, so if I would have represent here as like this, A1, A2 till AN. Now in this case, how many rows are there? N. How many columns are there? 1. So this becomes your column vector. So a column vector is going to have n rows and one column. On the other hand, your row vector is gonna have one row and n columns. This is basically going to be the difference. Now the same idea, you can always expand it to a matrix format where you can always draw a vector with m cross n, right? So you can create with the help of multiple row vector and column vector, where m is going to be a number of rows and n is going to be a number of columns, and you can represent this value. Now one interesting thing to note here is in your machine learning, okay, when we will be working on machine learning concepts, you will notice that most of the time whenever I will call something as a vector, it will always by default means column vector. Please keep this point in your mind because I will be using this a lot. So if I do not explicitly call something as a row vector, and if it's basically having definitely one dimension, basically it's having the value in terms of like n rows and one column, so it will vector will by default will be always be represented as a column vector. Just keep this in mind, okay, because I'm going to use this a lot, especially while deriving a lot of machine learning uh, kind of when I'm going to build a lot of mathematical intuitions behind linear regressions and so on. So just keep this in mind. Now, second thing, if I have to represent basically a vector, I can also represent a vector by defining a lot of basically spaces, bases, and so on. So what I'm going to do now, I'm going to explain you one more nice representations of vectors. Means you can always perform additions, multiplications, and so on. So, and this is really important for you to understand that how you can perform all these operations here. So let's go ahead and understand these operations. So when I say vector addition, okay, so it means what? It means, let's say this is my 2D space, okay, and let's say this is my vector A, this is my vector A, and this is my vector B, okay. And if I have to represent vector A plus B sum, it is going to be like this: vector A plus vector B, and this is going to be in the same format, okay. This is how you can represent basically the addition of two vectors. Now the question is, can I represent it in an equation way, that the way we are understanding these terms till now? Yes. So let's say I have two vectors. One is P, okay, which basically is going to be n dimensional vector. So I'm not now going with 2 and 3D in this, because now we have learned enough that we can represent a vector quite easily with the help of now with linear algebra in n dimension. So let's say a vector Q is there, which is going to be b1, b2 till bn. Okay. Now if I want to add these two vectors, let's say p plus q, the way they get added is they will just add the magnitude for it. So let's say it's gonna become a1 plus b1, comma, a2 plus b2, comma, so on. Similarly an plus bn, okay, like this. So this is how you can represent basically a vector in this manner. Now second thing which also comes up, like if you have a vector, so this is about addition, right? But what about if I want to multiply a vector with some scalar value? So let's say I have a vector present here, this is called as your vector A, and if I multiply with a value let's say 2, 3, 4, a scalar value which don't have any direction but just a number to it, so I can always do that, and this will turn my vector to different format. Look, let's say this will become a vector dash. So this is how also you can perform these sort of multiplication with a scalar value, right? So it's quite simple. So we got C vector A, and this is going to define your particular value in this case. Now similarly, a lot of times it do happens, let's say you have two vectors and you would like to multiply both the vectors, and that is called as dot product. So I'm going to talk about multiplication, and in multiplication I'm going to talk about dot product. In dot product, what happens? Let's say I have two vectors, x is equal to x1, x2. I have another vector y, which is going to be y1, y2, And if I have to represent a dot product of both these vectors, it is going to be x1 into y1 plus x2 into y2. This denotes your dot product of your particular vector. Okay, so just to give you one example behind doing this, and definitely you can now easily represent the same thing in a n-dimensional data. I am not doing it, but you can always do that on your own now after you have got an understanding of this. Now let's say I give you an example. Let's say vector A is having the value of 1 2 and vector B have the value of 6 15, and if I have to calculate the dot product of these two values, it's going to be 1 into 6, 2 into 15, and this is gonna be equivalent to 36, right? So this is the way you can always go and create the dot product of two particular vectors, which you can always do it like that. Now so we just understood that how to perform these vectors, additions, multiplications, and so on, right? Now the next thing is going to be that can I represent these vectors in a little different format also? Yes, you can actually do this. So let me explain you how you can represent it. So this is again coming up from your old maths. If you do recall your old mathematical time in your school days, this is what you were doing it a lot at that moment, right? So the same thing we are going to do. I can also represent a dot of two vectors like this. I can say dot of a comma b, and what I can do in this case is, let's say if I have to get the dot of these two vectors, one way is we have just learned that the way we can just multiply. But the second way also we can say that we will take the scalar of the value of this, okay, vector A. We will take the multiply with the scalar value of B vector into cos theta, okay, the angle between these two vectors. So if I have to represent it, you can represent it like this. So let's say this is your vector A, this is your vector B. So there's an angle theta between them, which I'm also representing it in this case. So this is how you can also represent your vector in this manner. So what does this mean, right? If you go back and see to this, what does this mean? There are two ways to represent. One is that if I have to take the dot of this, I can also represent it by A1 B1, okay, A1 B1 plus a2 b2 is equal to length of A. I'm not representing now a vector notation here. Length of B cos theta, right? So if I have to get the angle of theta now, I can say cos inverse, right, or arc of cos, which is going to be A1 B1 plus A2 B2 divided by length of vector A, length of vector B. Like this, we can actually define our data outputs. So that is also one nice representation using which you can define your values. Now there's a question for you. My question is, let's say the same thing what we had, we are doing it up. Now I have a vector A basically like this, okay, vector A like this, and there's a vector B which is going to be like this. But there's a catch here. The angle between these two vectors is 90 degree, okay. Now this vector A could be like A1 A2, right? It's a two-dimensional data, B1 B2, but it doesn't matter. You can think of it in an n dimension also. And if I ask you now the dot product of these two, now in this case what is going to be the output? You would say that A B cos theta, right? Cos theta. Now theta is what? Cos 90. Now cos 90 is what? Think about it. What is cos 90? 0. So in this case, your total multiplication value is going to be 0. So if two vectors have an angle of 90 degree coming up between both of them, then in that case it is going to be the dot product of them is going to be always 0. I hope this part is clear to all of you, because this is a very important thing which we have just learned. Similarly, there is also something called as cross product of two vectors. Let's talk about it. Now in a cross product, let's say I have two values, let's say x1 x2. There's second vector which is y1, y2. This is second vector. And if I have to basically get the value for it, I would say x1 into y2 minus x2 into y1. Okay, so this is how we can represent your cross product. It's quite simple, right? So you can always do the cross product of this. Now remember this very important point, that cross product is not commutative. Means if you are taking, let's say, cross product of a comma b, this is not mandatorily meaning that basically that it's going to be equivalent to cross of b comma a. Okay, so because there may be sign and all that coming up which will be a negative sign, so keep this in mind, guys, because this is going to be important property again which we will be using it while solving all this stuff. Now a question might be coming in your mind, can I code it and see whether this dot products and all, can I do it with numpy package? Yes, why not? So what you can always do is you can just, I will show you up how to perform all these statements. Okay, so what we are going to do now is I'm gonna write a code here which is going to help you in basically calculating the dot product of two vectors. So first thing is I need to import a numpy package. So I would say import numpy as np. Let's take two vectors. Let's say a vector, I can denote it by saying np dot array, and I'm gonna denote it with the value 3, 4, 5. Let me take another vector, let's say again np dot array, and I'm gonna take, let's say, value 1, 3, 6. Okay, let's execute this also. Now if I have to get the output of these dot product of these two, I can say np dot dot a comma b. So can you see that it's so simple to achieve this thing while just using a normal numpy package for achieving all this part, right? So it's very simple to perform and get all these outputs while working basically here. Now even if you take a 10-dimensional case, you can just very easily create a vectors, put it in the dot of numpy, and you will be able to basically get your outputs. So that's a very interesting point while you are working with respect to basically your numpy. Basically with Python makes it quite simple when basically you are solving such sort of problem. Now one more thing which I want to talk about is, which is very useful especially when you are going to work with respect to your vector operation, especially when you have to project something on one vector to another vector. So the way we do that is, let me in fact put down that statement for you. This is called as projection of a vector. So projection. And guys, these all things are just a revision for you. Okay, so I'm not going into too much of depth here. It is just for kind of a recall of your school maths, so that you can get a good intuitive kind of recall of all your concepts whatever you have learned, and then when we will go to machine learning, you will not struggle in kind of understanding any mathematical intuition, which I'm gonna also explain it to you there. Now let's say there are two vectors. Let's say this is a vector A and there is a vector B. So vector A, vector B. Now if I have to project of this vector A on B, means a shadow. Okay, basically what I mean is shadow. So basically shadow is going to fall like this perpendicularly, right? So I want to get this value. This is called as projection. Basically this value D is what I want to find out, that what is the value of this D if there's a vector A and B with an angle theta between them, and basically I would like to figure out that what is that shadow value in this case. Now in this case I can always define it, the value of D, with D is equal to, because this is the length of vector A, right? So this is the length of vector A. So D is equal to vector A cos theta. Again, you can always go back and define it with cos theta, right? So cos theta is going to be the D divided by this, right? This is what basically your basically this D value is going with, cos theta value is. So I've just kind of put this on the left hand side, and that's why I got D is equal to length of vector A cos theta. So this is one of the equation which basically is going to be important. Second derivation which we can always do is that if I have to represent this value here, so I can say this vector A dot vector B, if I have to multiply these two vectors, this is equivalent to what? This is equivalent to my A, length of A, length of B, and I can represent a cos theta, right? Now this is I have put the value of A dot B is equal to this A B cos theta. So let's basically play around my equation and put my value in this case. So what you will get in that case is, you can go back and always derive it. You can say that D is equal to, I'm just going to put the value here, A dot B divided by angle of B, because if you see it here, what I've done is I have just placed the value of vector A, okay, this value in this equation. Okay, so what is this going to be? D divided by cos theta. So cos theta will get cancelled, so we will be left with this portion, right? We will be left with basically this portion. So that's how we got it. So I just plugged in this value and we can get this. So this is also another way of representing my projection in this case. Okay, so these are the projections and all that which we gonna use basically while solving all these problems. Now one more thing which we will be noticing a lot while solving your vector equations, though this is kind of you will be using this term a lot, like you will be hearing about vectors, spaces, and so on. So what does this mean is that if you add, let's say, any two vector or scale two vectors, it will be always present in the same data set, right? So what does this mean is that if let's say I have a vector v and w, okay, and they both are in a vector space, and c1 and c2 values are, let's say, scalar. So what I'm saying is, let's say I have a vector v and w vector, let's say I have these two vectors, and I have two values, let's say c1 and c2, which are scalar values. Okay, these two are scalar values. Now if I have to represent, or I can also call them as constant. So if I have to represent an equation with respect to, or linear equation with respect to v and w, I can, let's say, if I represent it like c into v plus c2 into w, so the output what you're gonna get will also belong to the same vector space. Okay, so basically it will also belong to the same vector space, so it's going to be in the same format what we are basically going to work on. So this is again another thing which you will keep on hearing while we will be solving multiple problems. Now as I said, there are still a lot of things into it, but let's do one thing. In fact, you will keep on noticing all these things which I explain you have a very wide application into machine learning side as well, and you will notice that this is like a backbone of whatever we have learned. So we will do one thing. We will look at a few more things with respect to your linear algebra into your next lecture, and followed by that, then we will also talk about some more interesting concept with respect to other mathematics side like inferential mathematics and calculus for the time's sake.